today we have Polish researchers from ERA-Chair project joined our institute. Of course, just after the ERA-Chair holder, so Marzena Szybicka. Jack is enthusiast of haggis. He's from Scotland. So we can discuss Scottish kitchen with him. But also he's an expert, really very, very strong in numerical methods devoted to quantum many-body systems, also open many-body systems, which are usually very difficult to solve. He's from University College London, practically finished PhD. It's just the time when you have to wait for the defense, almost. Then he will go to United States, but during the 6 months we have right now, actually until September, I believe, Jack will stay in CFT, and it's perfect opportunity to discuss with him and to learn advanced numerical methods in quantum physics. So, Jack, the floor is yours.
Thank you very much. So I titled this talk "Methods for Simulating Open Quantum Systems on Two-Dimensional Lattices for Tensor Networks." But a significant portion, probably the majority, I'm going to spend my time introducing tensor networks and giving some background. And maybe a third will be spent on the title of the talk. And hopefully at this time, we'll introduce some new things we've been working on regarding long-range interactions. That's part of my PhD. Okay, so quantum many-body physics. So the simplest state we can write down in quantum mechanics is a qubit. So a quantum state that has two classical measurement outcomes. This could be the spin of a spin-half particle along a axis. And the most general quantum state is a superposition over these two classical measurement outcomes. In terms of these complex numbers, A0 and A1. We can add a second qubit, and now our general state is a superposition over all of the different configurations. So 2 in spin up, 2 in spin down, and then either or. So we have 4 complex numbers. And this allows us to construct entangled states using the combination of superpositions and 2 qubits. So for example, this state has no entanglement because these are the measured outcomes are entirely independent, even though they are the same in this case. So we can use this metric, entanglement entropy, to quantify this. And then this is an example of a maximally entangled state, which takes this value of the entanglement entropy of log 2. So when I measure 0, I get 0. Or when I measure 1, I get 1 milliparticle. So we can keep going, adding more and more qubits. So for 3 qubits, we have 8 complex numbers here to fully write down a general state. And as we go to n qubits, we'll have 2 to the power of n complex numbers. So the most general state of n qubits would be this in terms of these coefficients a. So to illustrate this scaling, I've got some examples of how much memory we would need on a computer to write this state down exactly. So for 20 qubits, assuming double precision complex floating point numbers, you need about 16 megabytes of RAM, which is, I believe, around 10 floppy disks size, about 1 million classical states. So add another 10 qubits, we now have about 1 billion classical states, 16 gigabytes of RAM, which is how much memory is on my laptop, for example. And we go to 50, this is about 1 quadrillion, I think. 16 petabytes of memory required, which is, so this is the most powerful supercomputer in the world currently. This has across all of its nodes around about 5 petabytes of memory, so it's around 3 times that. Double this, okay, I can only write this number down really. 10 quadrillion petabytes. I couldn't think of a good example. And then sort of the upper limit, 266 qubits. And this is around about the number of protons, this n Eddington number, the number of protons in the observable universe estimated. So this is definitely the upper limit of what we can do. And to see where we are in the state of the art, this is some sort of current generation noisy quantum computers, and you can see we have qubits sort of on this order of 266. So to continue developing these devices and improving them, understanding them, it's very important we can simulate these devices classically. But how do we overcome this curse of dimensionality? How do we even begin to approach this? But in the past 30 years, there's been a great deal of work theoretically into understanding the structure of this many-body Hilbert space. And the general themes that has come out of this research is that, so if we have our Hilbert space here, pretty much all of this Hilbert space is not physical. We have an exponentially smaller subspace containing the physical states that actually occur according to reasonable models we encounter. And then also
the criterion of the state being physical.
Okay, so specifically this definition relates to if I have a local Hamiltonian, what are the states that can be reached in polynomial time under the evolution of this local Hamiltonian. So a lot of these can only be reached with exponential time. So we say this is not reasonable, not physical. Also, entanglement tends to be limited. So what do I mean by that? Well, if we have a sort of lattice of qubits, say, or quantum systems in one dimension, then if I divide this into this blue and red region, and the size of this boundary is just constant, right? And if the entanglement between these two regions obeys an area law, then the entanglement does not grow faster than with the size of this boundary, which in 1D is constant. And this is in contrast to the more general volume law, where this entanglement energy between these two regions would grow with the size of the region itself. So in 2D, we now have the size of the boundary grows with one of the length dimensions, not with the length dimension squared. So we have volume law by L or something, sorry, these are on the order of L, on the order of L squared. And this might seem like an aggressive restriction to the entanglement, but in reality, there are many physical and interesting quantum states that obey this area law of entanglement, despite it being exponentially smaller than the entire Hilbert space. So examples are ground states of all gap models in 1D, any state with exponentially decaying correlations, again in 1D, and there's many more examples that you can prove of systems obeying the area law. So how do we parameterize this? Well, the answer is tensor networks. Okay, so some notation. In this talk, a tensor is a multi-dimensional array of complex numbers. That's all we require. So this is a tensor, the coefficients in this basis expansion is a tensor. And then it's useful to write this as a diagram where we have a shape, and then each of the indices are representing one of the dimensions of the multi-dimensional array. So here this would have n indices. And then, so another example is this rank, so this order 3 tensor, which has 3 indices, alpha, beta, gamma. And then if 2 tensors share an index, then what this means is that this is a sum over that index, so a tensor contraction. So this is just a matrix vector multiplication. And what we usually do is we just don't bother writing these indices in because they don't really carry much information. And then the shapes of these tensors can be arbitrary, or we can apply some meaning to it. So here I'm using the signal shapes to denote my isometry. And when I multiply these together on this side, this long side, I get the identity, which is a straight line. Also, these tensors can be reshaped. So I can move all of these S indices and group them together on one side, likewise T indices, to form a matrix. And then I can apply my usual techniques from numerical linear algebra to do things, such as the singular value decomposition to decompose this tensor into three other tensors. In this case, the SVD gives you two isometries and a diagonal matrix of singular values, which are positive, real and positive. So it has this kind of structure here, where the columns are orthogonal, the rows of this one are orthogonal, and we have a diagonal matrix. And this is useful because suppose we want to approximate this matrix with another matrix of lower rank. So the rank here is chi. To solve this minimization problem, then the SVD gives us this analytical solution to this. The optimal solution to this. So we have, and we obtain this by taking the SVD and throwing away, so only keeping the largest chi singular values. So we set all the rest of them to 0. And then essentially all we need to store then on the computer is this portion, and this portion separately, which gives us a memory saving, assuming chi is not d to the power of n. Yes, and the optimal low rank approximation for this matrix A is given by the truncated SVD. Okay, so suppose we again go back to our quantum state and we repeatedly apply the truncated SVD in an optimal way. What we'll end up with is a matrix product state. And then, so each coefficient in this state is obtained from a product of chi by chi matrices if I truncate chi. And this, we call this the bond dimension, and it's this finite bond dimension that limits the entanglement. So an example, this W state, which is the superposition over all the states with just one of the particles in the state 1. This has an exact representation of the matrix product state with bond dimension 2 in terms of these matrices here. And you can see this by noting that A0 is just the identity, and this A1 is nilpotent. So the only terms in here that have exactly one A1 are going to survive when I multiply out this product. And then each bond in this tensor network has bond dimension 2 because the matrices are 2 by 2. And this then allows you to see this property of the W state that is entangled across any partition of this one-dimensional lattice. That's because this bond dimension is greater than 1 everywhere. Okay, so to talk about the entanglement in a bit more detail, we have this inefficient representation of our many-body quantum state. We can take this singular value decomposition and define this as being a quantum state on the left side and likewise on the right side, indexed by I. And then this is just then the Schmidt decomposition of this state. It's exactly the Schmidt decomposition. Then the entanglement is given by the Schmidt coefficients, which are real and positive. And you can see that this is then going to be bound by something on the order of n. Like a logarithm or something goes to the power of n. With the matrix product state, on the other hand, because each of these bonds has dimension chi, our entanglement is now bound by log chi. More importantly, something independent of n. So this is the area law. And essentially the entanglement entropy in a tensor network is proportional to the number of bonds cut. So there's all going to be order 1. We can, for example, construct a fancier tensor network. I'm not going to expand this acronym, it doesn't matter. Where we have log 2L layers. So to divide this region here, I need to cut through log 2L bonds. So this allows us to represent logarithmic corrections to the area law, but not volume law. Okay. An example of an algorithm that you can use with tensor network ansatz is this time evolving block decimation. There should be an equal sign here. Apologies. So if we have a nearest neighbor Hamiltonian, in terms of, yes, nearest neighbor terms, we construct the time evolution operator and then do a Fizyki trotter decomposition where we take this sum into products over terms with some error, the tau. Then the tensor network, essentially, that the time evolved this state looks like this, and we just contract this repeatedly. Okay.
Sorry, so maybe I missed something. So till now we were talking about how you represent a state in a very efficient but approximate way. So how do you do the gates on this? Maybe I missed something.
Yeah, so how do you represent these?
Yeah.
So this is just an exponentiation of a 2. So the matrix that is defined like a local term. So in this case, say it's an Ising term, it would be Pauli Z.
Okay, yeah.
Quantical product with Pauli Z. And you just exponentiate this. It's just a matrix, yeah.
I have actually a similar question. Following the question just asked, we understood more or less that some quantum states can be represented with this tensor networks. Of course, we have to do approximations and we end up with such states that obey this area law. What means that you are somehow restricted to unaccounted subspace. And then if you do these operations, we have to also assume that these U operators, they can also be efficiently represented.
So
It means that you are also limited concerning the dynamics in general.
yeah, so in general, yes. So you can see that this construction of these 2 local operators can be represented as a tensor network, essentially. You can imagine here we have a bond that has bond dimension 1. It doesn't do anything. So a general non-local term won't necessarily be able to be written down in terms of this decomposed local structure. But for nearest neighbor Hamiltonians, it can be, just trivially, by taking tensor products of local terms.
So, pardon, basically, local Hamiltonians are easy. They are assumed easy, right? It's the global entanglement which is difficult.
Yes. In what sense?
You don't have to do anything because basically here with the gates, because you have a 2-qubit gate, which you assume it's easy to simulate.
Yes.
But n-qubit state.
Yes. That would be inefficient.
So that's why you don't work with the gates, because you took them local and then you assume they are easy to simulate.
Yeah. This Fizyki trotter decomposition allows us to write this massive unitary in terms of local products of easier to deal with unitaries.
Yeah, and also regarding, because you see initially you started off saying that there are states which you cannot represent, right? So here also, when you start off, you need to represent that huge matrix to start this decomposition process. So how do you do that?
So in reality, you don't take the state exactly and then do the SVD. You would construct a sort of ansatz, and then you would run some algorithm which would give you some initial state. You very rarely will construct the matrix product state directly. Usually you would start with the product state, evolve it through time, say, controlling this bond dimension, and then up with some output matrix product state with some larger bond dimension, say. Yeah. Okay. So what about high dimensional situation, high dimensional tensor networks? Okay, so if we have a 4x4 lattice here in 2D, If we just naively apply a matrix product state to this, we have to choose some path. So we've chosen the snake path. And you can see that we can partition this two-dimensional lattice with this structure into two halves by cutting only one bond. So we only have to cut this bond to divide this in two. So this means we can only represent entanglement up to a constant, which is not area law in 2D, because area law requires in 2D order one power of the dimension, order L. So we can solve this by introducing this projected entangled pair state, PEPs, where we have bonds between all of the adjacent tensors. And you can see now to divide this into this left side and this right side, I have to cut 4 bonds or a number of bonds on the order of the length of this system. So the boundary. So this allows us to represent area law in 2D. But working with PEPs is way more difficult than MPS. Okay, so this is a statement. I removed the slide that had the prerequisite knowledge of this, but with a matrix product state, there is a statement you can write down regarding if I have 2 matrix product states, under what conditions do those represent the same quantum state? This is encoded in this fundamental theorem of matrix product states. For PEPs, we do not have this, and this is sort of fundamentally problematic in many ways.
Excuse me, could you please define this projected entangled pair space?
It's a tensor network with bonds with a bond dimension greater than 1 between the nearest neighbor's sites. The name comes from its original construction in terms of you have a virtual particle on each of the bonds, and these tensors project those virtual particles onto the local Hilbert space. But it's kind of superseded its original naming in terms of how it's used. It's just the 2D generalization of MPS, essentially. Also, because we have loops, we can no longer partition this tensor network into 2 halves by cutting 1 bond. This is problematic when truncating states. It's also inefficient to contract in this sharp P complexity class. If I was to contract all these bonds, this is not possible efficiently. Also, it's not as expressible relatively compared to the MPS. So what I mean by that is if we have our 1-dimensional Hilbert space, our 2-dimensional Hilbert space, and we have our area law states in here, the MPS roughly parameterizes all of the area law states. For PEPs, this is not the case. There are states that obey area law that cannot be efficiently represented with PEPs. So this is exponentially smaller than this, is exponentially smaller than this. But nevertheless, these high dimension methods are still very successful. So there was this sort of quantum supremacy result from a couple of years ago, where they simulated a particular easy model and used some noise extrapolation to sort of propose this as a quantum supremacy, that this could not be simulated classically. And then a few sort of, not even 2 weeks later, this paper is published or submitted on the archive, where they indeed simulate the results of this paper using a tensor network. So the experiment they were doing is they have this processor, this Eagle processor at IBM, in this heavy hex geometry, and they were basically simulating dynamics under this unitary. So you write this down as a tensor network like this, respecting this geometry, and then it was showing that, so the IBM experiment is these error bars, and you can see that the tensor networks do some of the tensor networks do very well simulating this. So there's a whole flurry of results of tensor networks successfully simulating this quantum supremacy claim. These ones are yellow because these are the ones that aren't very accurate. Yes. And the reason this was so successful, so amenable to being simulated with tensor network is because of this geometry, fundamental geometry of this processor where we have very sparse loops. So, example here, most of these tensors only have two neighbors, and there are some other reasons as well. Okay. Yes.
So till now we have been talking about qubits, which does not have any statistics problem. So if we try to do it for, like, say, for fermions or bosons, what change, or will it work?
So bosons there is no change. You just have to consider some cutoff in your local Hilbert space. Fermions, the only change is bookkeeping, in that you have to keep track of these signs when you permute indices in the tensor network. And this is very non-trivial, but it's possible. There are software packages that do this for you. It is a considerable amount of effort, but it is possible.
Because my doubt was whether the SVD would preserve the nature of the statistics. That was my, because that's what you're relying on, right?
Yes, it will, provided you're taking care of the parity of fermions correctly, which is non-trivial to do, but it is possible. I wouldn't recommend coding that from scratch. There are packages out there that will do that for you. And then you have to be careful about the way you construct your tensor networks, that you're respecting this, but yeah. Okay, yes. Okay, so what about open quantum systems with tensor networks? That's what I was going to talk about. Okay, so why do we care about open quantum systems? Well, any quantum system in the lab is never going to be perfectly isolated, invariably going to interact with this environment. This is unavoidable. So we need to understand these systems. So it's an open system rather than a closed system. We should understand this to A, mitigate these effects if we want to do that, or harness the distributive nature of an open quantum system. For example, you can use distributive systems.
We are all the time in 2D, yes?
Yes, yes. I work on 2D systems, but tensor networks generalize to higher dimensions. So there's some applications where we explicitly use the dissipation for some purpose rather than trying to mitigate it. So an open quantum system, we have our system, we have an environment or a bath. Both of these evolve according to their Hamiltonians, and then this interacting Hamiltonian here. And here I'm using a generalization of a quantum state, this density matrix, which allows us to include classical ignorance into our statistics, measurement statistics. So this whole composite system will evolve according to the Schrodinger equation, or in terms of the density matrix, this von Neumann equation with this total Hamiltonian. And then the dynamics of the system only can be obtained through tracing out this path, so averaging out the dynamics of this path, which you can see in these diagrams as contracting, taking the trace of these indices, and we'll end up with this equation for the system dynamics only. And then a particular physical situation can be obtained by considering a very, very large bath relative to the system, and assuming we have very weak coupling from the system to the bath, and rapid bath dynamics. So we require that the system does not change the eigenstates of the bath, and also that any correlations that go into the bath dissipate at a rapid timescale relative to the system. And under these physical assumptions, we can make the Born approximation where at any time our density matrix will factor into a product state between the system and the bath, and also the Markovian approximation, where the state at time t plus delta t only depends on the state at time t, not on any of the previous history of the states. And then under these assumptions, with these approximations, we can derive this Lindblad equation, which is the most general Markovian equation for the density matrix evolution. And we have this von Neumann coherent part, and also this dissipative part in terms of these jump operators, which usually you can derive these microscopically, but usually they're just chosen based on the problem you're trying to solve. So we can have dephasing, decay. This could be also annihilation operator, whatever. And yes, so and the general sort of intuition here is that this part will generate entanglement, and this part will remove entanglement. And this is what we rely on for our tensor network to remain tractable throughout time evolution. That this is strong enough to damp off this entanglement and keep us in the areal regime. So our goal is to find solutions to this Lindblad equation on two-dimensional lattices. So we have our tensor network here, and I have an extra physical bond here because it's a matrix, density matrix. And I'm going to consider only systems in the thermodynamic limit. So I take this unit cell here, and I only consider this unit cell. And what we can do is vectorize the state and this Liouvillean superoperator, this L. So here we have two physical indices. Here I'm going to merge this with this other index. You can, in terms of these diagrams, you have this density matrix that gets transformed using the superoperator. Now we just write this as a matrix vector.
Pardon, so where's the environment? That the rest of the lattice, or the environment is outside of the lattice?
So the environment has been taken care of when we derived the Lindblad equation.
So
We traced out the environment, yeah.
You traced out the environment, and the lattice is after the tracing.
Exactly, yeah. This is the system density matrix, yeah.
All right. So initially that was the lattice, environment was somewhere outside of the lattice?
Yeah.
Yeah.
All right, so the environment is not part of the lattice?
No. Yes, exactly.
Okay, thank you.
This is just the system density matrix.
Okay, thank you.
Okay, so if we do this vectorization procedure, then we just have a linear algebra problem essentially. So we can apply our trotterized evolution to each bond. So here we have, okay, so I should have mentioned, assuming a two local Lindblad equation, so two local operators, nearest neighbor operators like we had before with the TEVD. Now we have these across the even, x, odd x, etc. bonds. So we can apply these in sequence like so across these bonds to the odd along x, which is this bond, which is periodic. Likewise in the vertical direction, etc. And our hope or intuition is that if the dissipation is strong enough, entanglement should remain tractable and our tensor network should remain valid. And indeed, this was done 2 years ago. So if we have this dissipate easing model in terms of this transverse dissipator here, so it's dissipation along the x direction. This is exactly solvable when we have no transverse field. But also its steady state does not commute with the Hamiltonian, but it's non-trivial. There's frustration there. So it's a good model to study. And you can see that, so we have the exact solution in dashed here. And as we increase the bond dimension, our simulation aligns very well with the exact solution in this regime here. You know, you get a larger bond dimension. Of course, as we get to very large interaction strength, so relatively weak dissipation, the tensor network begins to fail, and that's sort of expected. And then we can also look at the non-exactly solvable regime when we have a transverse field and see that things are converging with the bond dimension, which is good. Okay. Okay, so what about long-range interaction? So before I've only been discussing nearest neighbor Hamiltonians. how do we go beyond this? Well, first of all, why do we care about this? Well, in recent years, quantum computing has sort of accelerated with based on atoms, so trapped ions systems. These have become really successful and sort of arguably overtaken systems based on superconducting qubits, for example. And these have these kind of long-range interactions in trapped ion systems, where this P parameter here is tunable. And for example, this 2-qubit gate fidelity continuum claims to have a device which has this 2-qubit gate fidelity above 99.9%. There's 3 nines, which has been a long-standing engineering goal in quantum computing. And this was done with these trapped ions. Also, you can have a platform based on neutral atoms, which evolved according to this Rydberg Hamiltonian, which has this van der Waals interaction strength to the power of 6 here. Also a transverse field, say, and this detuning. This R sub B is this Rydberg blockade radius. And you might think that this is a very short-ranged interaction. Why can't we just consider this nearest neighbor? Well, what you find is that by properly including this long-range tail in the van der Waals interaction, you get significant modifications to the phase diagram here. So this is where we truncate it beyond a distance of 2 in the lattice. So this is very different to this. So it's important to take this full long-range tail into account. So how do we do that with the tensor network? So remember we had this 2-qubit, 2 local gate situation with nearest neighbors. We can go beyond this by considering also a tensor network time evolution operator. So we represent this as a more general tensor network, and this allows us to study long-range interactions. I'm not going to go into, yes.
Including Coulomb?
Coulomb, yeah, define Coulomb.
1 over.
Well, okay, so yes, but not in the thermodynamic limit, because that would not be defined. And I will say that this is, you do this by approximating this power law decay. And the approximation to this power law decay will get worse for the smaller the alpha. So Coulomb challenging.
So because earlier I got the impression that we are using local gates in
Yes.
this approach. So how are we sure that we can represent this long range interaction, which is a unitary, in terms of local gates?
We can't represent it in terms of local gates. Well, local in the sense that they only act on 2 sites at a time, but they are long range. Yeah, and you'll just have to believe me when I say we can construct tensor network operators that represent these kind of interactions. There's a lot of technical detail behind that, but basically this is much more versatile. So an example, we have the displacive long-range easy model with some alpha here and longitudinal dissipation. This is exactly solvable to this initial condition with spins aligned along X. This is a normalization dependent on alpha, which is essentially the sum over all of the interactions, such that when I change alpha, each site will still see the same overall interaction strength. So this just allows us to compare the simulations at different alpha properly. And the exact solution is this dashed line, and we can see that for sort of low interaction strengths, it agrees very well, and it's able to properly resolve this long-range tail here. And as we expect, it gets worse as we increase our interaction strength, and also as we increase alpha. And you can see that this is sort of a proxy to the entanglement entropy that for this large interaction strength, so weaker dissipation, this spikes a lot more aggressively before being damped off by the dissipation. Okay, so one of our more interesting model, we have this anisotropic XY model, which has been studied with again longitudinal dissipation, but now we have this in the perpendicular direction. This is being studied in the short range limit. So when alpha goes to infinity, using Keldysh field theory and also the tensor networks, and it was found that the mean field predicts a fictitious U1 symmetry breaking phase, which does not exist when you include the quantum fluctuations. And this is defined in the thermodynamic limit, obviously. The other end, as you can see here, we have this at the mean field, symmetry breaking. As we increase our bond dimension in our tensor network, this disappears. The other end of the spectrum, we have alpha very, very long range. Alpha equals 0 would be all-to-all interactions. Here we expect the mean field to be accurate, and we get to a Z2 symmetry broken phase here. And this is not defined in the thermodynamic limit, because this alpha, we end up with diverging interaction strengths, so non-extensive quantities. So we can't really simulate this in the thermodynamic limit. What about this intermediate regime where alpha is between these two values? Okay, so here the thermodynamic limit is defined, but we don't really know what's going on. We can use the tensor network to study this. And what we find is in the steady state, for small enough alpha, so long enough range interactions, we get a re-emergence of this symmetry breaking. But this is a Z2 symmetry broken phase. So alpha equals infinity, we have this previous result where there's no ordered phase, whereas here we have this ordered phase. But with corrections to the mean field, so the mean field in the dashed line. So we can begin to sort of maybe start filling this out approximately, getting some insight into this regime using this tensor network. Okay, that's all I wanted to talk about. And summary, I won't read these out, but if you're interested, I have a package for doing these kind of simulations. It's not public, it's private, but anyone who wants access, just let me know. The reason it's not public is because not all of it's working yet, so I just need to make sure people know that. But I'd be very happy to talk through with anyone interested on how these simulations work and how to run them using this package. Yes. Okay, thank you.
Thank you for taking the time. Now we have time for questions. Please.
In some sense, the most fundamental multi-particle property system is just the multi-electron atom. Are these methods also penetrating the area of quantum chemistry?
Tensor network, absolutely. Yeah. 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 I'm not that familiar with that, but I'm aware that
What can be computed
in quantum chemistry,
efficiently or more accurately than quantum chemistry methods?
I'm not sure regarding quantum chemistry precisely. I would need to do some reading and come back to you on that one.
Because obviously these are very far from true level systems.
Yeah. Yes, of course. I'm not so sure about that. I would need to get back to you on that one. Sorry.
I'm not quantum person, so maybe my question will be stupid, but I understood that at some point you discussed the interaction of your system with surrounding, and then you assumed weak coupling, which I guess this is what you generally want, but then you assume that the surrounding evolves much faster than the system. I would think the opposite, that the system will evolve slowly because it's much larger, just like that.
The idea is that any information you put into the environment just disappears quickly and is irrecoverable. It can't then persist and then back propagate into the system at a later time.
Just because a huge number of degrees.
Exactly, yeah. So things just get washed out immediately on a timescale much faster than the timescale that the system can evolve. So within one relevant time step to the system, everything's already dissipated into the environment. So that information is now lost. That's what we mean by rapid dynamics.
So thanks for the very nice talk, first of all. And this dissipation idea, which damps entanglement, so it makes it more trackable. Do you use some sort of estimates? Like you try to estimate how much long-range entanglement is being damped by in a particular model, or you basically go sort of like hand-waving heuristically?
Yeah, it's very difficult to. The statements regarding area law with Lindblad evolution are very few and far between. Generally, things will break catastrophically when your tensor network has too much entanglement and can no longer represent your state. But we just sort of hope for the best, and provided things converge, we are more confident that our simulations are.
So it's more like by trial
Yeah.
and error to see if you are able to fit in the dissipation regime that you are interested in.
Exactly, yeah.
Okay.
What's the last sentence meaning? This one, dissipation.
This one?
Yeah.
Basically, without dissipation, our entanglement would grow usually unchecked without limit. And this would break the tensor network assumptions, essentially. So the
What does it mean? Why it breaks the tensor network?
because the tensor network assumes limited entanglement because of the area law. It's an efficient representation of yeah.
But the network has the error law, but the states may have a high entanglement.
Yeah.
But if you use tensor network, you approximate that, and this is your first assumption. And if you use that, it means it's satisfied. You assume that error law.
Yes.
Yes, and what's the relation about the dissipation? I don't understand.
So the dissipation allows you to remain in your quantum state, so not the tensor network, the quantum state in a regime that it still obeys area law, such that my tensor network is actually going to be a good approximation to that state.
Yes, but it has no relation with dissipation. Even if your dissipation is large or not, it depends on your concrete system. And it doesn't have relation with your
Dissipation damps entanglement, usually.
Usually, yes, that's correct.
No, but this is what Jack said, that they hope.
Yeah.
Yeah,
They hope to fit into the entanglement short range entanglement.
Yes.
If it doesn't work, then it doesn't work.
Yes, I understand. That's why you say usually. It's not correct if it's not correct if we assume that dissipation will kill entanglement or not.
You're absolutely right. It's not a formal statement.
Yeah.
It doesn't.
Sure.
Yeah.
It's not
It's not a
it's
formal.
not a formal. So I can imagine such dynamics that still will keep me in the error law, and then I do not
Yes,
need
and-
this dissipation.
Yeah,
I
that's
understand
why.
it's practical.
You can construct many dissipative systems that will not have this, will not be trackable tensor network. That this won't apply. You'll run the simulation, everything will break, and you'll think numerical instabilities will keep in. We hope that this is the case, and what we find when we run our simulations is that generally it is the case, provided we're constructing sensible models.
Maybe it's can be postponed for the longer discussion, but I have seen that there's a question from Oliver.
I didn't have a question. I just had a kind of
Okay.
trivial comments on a previous question, which was the question about this assumption that goes into the Markovian assumption that goes into the Lindblad equation. I mean, it's an assumption. It's not always true that this works. But it does work quite broadly. Essentially, is all I want to say.
Yeah.
There are certainly situations where there's an assumption that your environment in all scripting will fail, and the Lindblad equation will not correctly model your system, but it works pretty well.
Yeah, there are, yes. In fact, there are tensor network methods that can work in the non-Markovian regime, for example, which I've not discussed. But here I'm assuming these assumptions apply to the system I'm interested in, such that I can use this method.
One question. So can we adapt this formalism to deal with continuum modes, let's say for photons?
Yes.
Because in some cases we might know, like, okay, these states are important, so can we adapt it somehow?
Continuum in What's
modes, yeah, like.
in the modes?
Yeah.
Yeah, so I'm imagining you'd have to define your local Hilbert space, right?
Local in where, like in space?
In space, yes. But if you didn't have a local, say I don't think anyone has looked at, say, a tensor network in mode space. This may be something that would work and be interesting. I'm not aware of anyone looking at this.
If your degree is the polarization, then it is trivial.
Yes, yeah.
But if it's a color, that's harder.
Right.
Because my intuition is like the state of a photon, even in the, let's say, like discretize it for a moment. It's if you write it, it will look like the state that you started with, right? Like some tensor coefficients. With
Yeah.
some basis of modes. So that's why I was asking if you can.
Possibly. Maybe people have done this. Traditionally, tensor networks are discretized in space, so the network is defined with respect to space, not with the modes. But for example, with the non-Markovian simulations of tensor networks, they also have a tensor network in time, which characterizes this memory. So I think there's maybe other more novel ways of employing this decomposition, not just in space, for example. But I'm not aware of this.
Because I got the impression that it's not the space that is important, it's just a parameter space, right? So
Yeah.
it just depends on what you call those indices, right? And what.
Exactly, yeah.
If it's space, it's space. If it's modes, it's modes.
Provided the entanglement has this area law property between whatever those regions are, whether it's in space or in time or whatever.
Because the reason why I was asking is then you can maybe try to do the whole simulation for the system plus one.
Yes.
Yeah. So.
Let's paint the sticker again.